Hi everyone, today I will introduce a new framework that reconstructs 3D shapes into structured code. Imagine you're a furniture designer and you came across a beautiful chair in the market. Naturally, you want to know more about this chair, like how it was built, how many components it has, detailed parameters, joint information, and so on, so you can rebuild it or even modify it. This analyzing process is called reverse engineering, uncovering an object's details. And that brings us to our central question. How can we get parametric information from 3D shapes and even make them editable? So let me introduce MeshCoder. As input, we start from object point cloud. Our inference model translates it into part-by-part blended Python code, where each part of the object has its corresponding code block. Running the code in Blender reconstructs the whole 3D object, and since it's represented as code, you can easily modify it by changing parameters. MeshCoder not only outperforms previous methods by some standard criteria, like category diversity, topology quality, or reconstruction accuracy, but also offers two unique advantages. It's editable and can help with large language model understanding. There are actually many existing methods on 3D reverse engineering. For example, 3D scanning plus mesh segmentation. These methods can label the parts accurately. However, they provide no parametric details and so no editability. As for the program-based methods, they are elegant to show the shape logic, but usually they are limited to toy examples and simple geometry, and so no practical industrial usage. So, how did MeshCoder make a difference? Our first step was to design a new structural shape language built directly on Blender's industrial-level Python API. We define our own domain-specific language, also called DSL, on top of Blender's API. It supports 5 key operation types: primitives, basic building blocks like cubes, spheres, or cylinders; sweep or translation, extrude a profile curve on a path; Boolean operation, add or subtract shapes; loft or bridge loops, smoothly connect curves or profiles; array, repeat patterns. With just these 5 operations, we can represent most daily objects. Next comes dataset construction. Our goal was to build a dataset of point cloud, code, data pairs. But more importantly, the dataset should be structural, broken down part by part. It should be something like this. And that way, the model doesn't just see the whole shapes, it also learns how the objects are structured. We adopted a dataset pipeline, starting from constructing the part-level dataset. Then use the dataset to train a part-level inference model, and then we use the part-level inference model to construct an object-level dataset. So how do we construct a part-level dataset? We start from using the code generation programs. These programs are drafted by GPT and then refined by human experts. Then we execute them in Blender to get a 3D mesh. After extracting point cloud, we are able to get the desired point cloud code data pair. And using this, we can train a part-level inference model. Then we can scale up to the object level. We use the object dataset from Infinity Indoors, a large procedurally generated dataset where every object is cleanly segmented into parts. And for each object, we run the part-level inference model on its components, then assemble the results into a full program. The output is a complete Blender script for the entire chairs, tables, lamps, and beyond. And in this way, we are able to construct approximately 1 million point cloud code data pairs over 41 categories. Now let's talk about the inference model. The part-level inference model and the object-level inference model are actually within the same architecture. They are composed of 2 components, a shape tokenizer and a code generation model. We start from 3D point cloud. First, we project it onto 3 orthogonal planes, xy, yz, and zx. Next, each of these planes is divided into small patches, just like how Vision Transformer processes images. Every patch becomes a token. Then, we pass all those tokens through transformer blocks. This let the model capture global dependencies, so it doesn't just understand local patches, but entire shape as a whole. After that, we introduce a small set of learnable query tokens. Through cross-attention, they gather and compress information from all the patches, forming a distilled summary of the shape. Finally, this process produces a compact, fixed-length sequence of shape tokens. These tokens are expressive, lightweight, and ready to be fed to downstream modules like code generation. For code generation, we used a fine-tuned large language model, Llama 3.2/1b with LoRa. It also regressively generates symbolic programs from these shape tokens. Because it's not our main focus, we will keep it brief here. Now we turn to experiments. We evaluate using two metrics, chamfer distance, average nearest neighbor surface error between predicted and ground truth points, and IOU, the intersection over union of their voxelized volumes, measuring coverage overlap. By these metrics, our method is often stronger than prior work across categories in reconstruction accuracy. So, to summarize, our contributions can be illustrated into three parts. First, we provide an expressive Blender-based DSL capable of representing complex operations. Second, we provide a large-scale dataset pipeline, producing millions of point cloud code data pairs. Third, we provide an inference model that combines a shape tokenizer with a fine-tuned LLM to translate 3D point cloud into executable code. Ultimately, MeshCoder introduces a new paradigm for representing 3D shapes, which is editable, interpretable, and semantically meaningful, all through the power of our code representation. Thanks.